actually input to these algorithms, run somebody else's code, and then get the output from them and kind of understand their failure modes, but not go into the gory details. Is that fair? If you're disappointed, we can like hold a special section and go over these things in detail. Although you'll see in the course notes that I actually screwed up trying to derive one of these things that I wasn't planning on doing in class anyway, but I got excited on the airplane and gave it a shot. Anyway, so remember Boyden's algorithm? Yeah, remember Boyden's algorithm? Yeah, good. Right, so Boyden's algorithm said, okay, we really want the derivative, the Jacobian of a function from Rn to Rn, right? But we unfortunately, we'd like to use this secant style update, right? Where I have f at the previous data point and the current data point, I draw a little secant line through them and I use the slope of that secant as a proxy for the derivative of f along that line. Yeah? Well, we can do a similar secant style update here, where now we say, okay, our Hessian times the difference of x's that we've just seen. Well, remember the Hessian is the second derivative. Yeah? So really, this should be the difference of gradients of f's that we've observed at these 2 points. So now you can see why we at least assume that we have gradient of f, because otherwise we're in a little bit of trouble. Yeah? Does this update make sense for b sub k? It seems completely reasonable, all that. Yeah? But there's a humongous problem, which is that if I run Boyden's method, I could run Boyden's method. I could use exactly the same update. I could use quadratic Newton-style steps. I would converge to something. In fact, often this does converge. But we know more about the Hessian than we knew about the Jacobian. And unfortunately, this update procedure doesn't respect all the things we know about the Hessian of a function. Can somebody give me a property of the Hessian of a function? Just one thing. Symmetric. The Hessian matrix is symmetric. Is there any reason why something updated using Boyden's method should be symmetric? No. Absolutely not. Well, okay. So so we say, okay, we have to go back to the drawing board and think about our optimization techniques. And we'd like that our approximation b sub k, the Hessian of f, at the very least should be symmetric, and we really like it to be positive definite. Right? Because we want to avoid this case where we zoom off to the maximum. Yeah? In fact, we'd almost rather flatten f in directions where it's increasing than have this matrix be positive definite. Huh? Well, okay. So we can do the obvious thing, which is we say, okay, go back to Boyden's method. Remember what Boyden's method did is he sort of had this viscosity term, right? He said, okay, change my approximation of the derivative as little as possible while still satisfying the secant style update that I have, right? I can say, okay, well, disregarding, like for now, we don't really know what it means to add a constraint that a matrix is positive definite. Turns out that it's convex, by the way, but that's a very advanced topic. But I can say, okay, change b as little as possible, and keep my secant style update just like Boyden's method, and add one additional thing, which is that b is symmetric. Yeah? And this algorithm has a name. It is called the Davidon-Fletcher-Powell algorithm. Right? And given your homework problem 1 on how to derive Boyden's method, this is no harder to derive. Right? It looks like almost exactly the same optimization. Very popular method, but unfortunately, it has one kind of bizarre property. Now, remember that Newton's method basically is updating my iterates by applying the inverse of the Hessian times the gradient of f. Right? That's the formula that you guys really should remember. Very important. But we added a viscosity term that says the Hessian doesn't change that much from iteration to iteration. Yeah? But that's not necessarily what's actually going to figure into how well our algorithm behaves, because in the end we're going to invert that Hessian matrix. Yeah? And it turns out that just because the matrix itself doesn't change very much, the inverse can actually change a ton. In fact, we can see this by just looking at one-by-one matrices, that is, at numbers, right? For example, I'm going to give you two numbers that are actually pretty close to each other in the scheme of things, and their inverses are very far apart, and those two numbers are 1/10 and 1/1000. Right? These numbers are very close to 0, but 1 over these numbers, hopefully you guys can do this calculation, is quite different. Right? So kind of an unfortunate property of this, Davidon-Fletcher, whatever the heck, Davidon-Fletcher-Powell algorithm, DFP, is that you can actually take accidentally really big changes from iteration to iteration of what your algorithm is doing because you care about the inverse of b sub k rather than b sub k itself. Yeah? So this was our motivation for deriving a slightly different algorithm, which is actually still pretty similar to our Broyden story, with a little bit of a twist. So remember the Broyden story, we noticed that our Broyden updates actually could be written as updates on the inverse matrix itself. Yeah, in fact, you're going to derive those updates on problem 1C of your homework. Thankfully, it's not too hard, I promise. And we could do a similar thing here and just keep track of BK inverse instead of BK. Yeah? Now, in Broyden's algorithm, BK inverse was really the inverse of the thing that we were updating in primal space, right? It was just a convenience to avoid having an inverted matrix. But one thing we could do is actually ask that the norm of the difference of the inverses of BK, did that parse? Remember, we're gonna carry around BK inverse. So we're basically gonna try and minimize that second norm there instead of the first one. Yeah? And so what we can do is define a matrix H sub k, which is the inverse of B sub k. Yeah? And we're going to say, okay, we actually want the difference of H sub k to be small. It's very easy to check that a matrix is symmetric if and only if its inverse is symmetric. So that's what the first condition here is doing. And the second condition, well, let's go back to our DFP update. Right? Remember that's b times the difference of x's equals the difference of gradients. Yeah, this is our favorite secant style update. Yeah. Well, let's say that I multiplied this by the inverse of b on both sides. Right? Then the difference of x's would equal the inverse of b times the difference of gradients. Yeah. And that's exactly what we do. Let's see. So right. So we're gonna put the inverse of b on the right hand side now instead of b on the left. Yeah? This is not the same iterative scheme as DFP, right? Because the norm that I wrote down on the top there is the norm of the difference of inverses rather than the norm of the b's. Yeah? This algorithm is called the BFGS algorithm. I won't even try to remember what all those letters stand for. It's a bunch of 4 different people that all invented this at the same time, and it is state of the art for optimization. Chances are, if you want to optimize a function out of the box and you don't know anything about this function, now if you know that your function is convex or something, it's a whole different story. But if you don't know anything about f and you want to find its minimum, chances are you'll be using BFGS. And that's because it only requires one derivative, it has very good convergence properties, it looks like Newton's method, and so on. Yeah? Now, of course, I give you a warning that this was advanced material, and you kind of say, well, this doesn't look so bad. Right? I mean, this looks awfully like the things that we already know. Now, first of all, I haven't proved to you that any of these algorithms actually converges. That includes Broyden's algorithm. Right? We have some intuition that it should, but we actually had to write a rigorous proof of this is a little bit hairy. But also, there are a couple things that hopefully at this point in 205 you should be getting suspicious about. Which is, first of all, I didn't put a subscript next to that norm. Right? This norm, hk plus 1 minus hk. And it turns out that in order to derive BFGS, you need a very special choice of that norm in order to make this optimization tractable. In fact, you'll notice in my course notes that I tried to derive the BFGS update. It failed a little bit. I had a sign mistake somewhere. The first student to find the sign mistake will get copious amounts of extra credit and so on. But the basic philosophy here is simply this. It's very similar to the Broyden update. Oops, that's not HBK minus 1. That's HK minus 1. Sorry. But the philosophy is very easy. It's very similar to Broyden, but now we're going to deal with the inverses and ask that the inverses sort of be viscous instead of the Hessians themselves. No? So what is the input and what is the output to BFGS? The input is a function f, and the first derivative, the gradient of that function f, but not the second derivative. That's going to be approximated with hk. Yeah? And an initial starting point x0 of where we think the minimum is, and then BFGS is just going to iteratively update Hessian, and then do a Newton step, and then the Hessian, and then the Newton step, Hessian, Newton step. Yeah? In fact, one slight change from BFGS, that can have better behavior, is you do the Newton step, and then you look, so that, I'm at xk, that gives me xk plus 1, And now I do a line search between xk and k plus 1 to try and minimize a little bit more. Yeah? So all kinds of nifty tricks you can do in the world of optimization to try and find minima. I wanted to sketch out a couple so that you have at least enough tools to get started and some sort of holistic understanding of where to go from here. But for us, our main goal in 205A is for you guys to be clients of this machinery. And in fact, on your next problem set, I'll include 1 or 2 applications of optimization and maybe even have you code some of them up just so you can appreciate how painful it is. By the way, just like we talked about in BFGS, or rather in Fgs Algorithm, remember I mentioned there's a limited memory option. We only keep track of a couple iterates ago and kind of construct your approximation of the derivative just from the last few steps. You can also do the same thing in BFGS by applying exactly the same trick. Just FYI. Okay. So that's the end of our unconstrained but multivariable optimization story. Yeah? Are there any questions? Because we're about to move on to optimization part 3. Unfortunately, I only get a week on this material, and I gotta move on because 205 has this ridiculous pace. Yeah? Cool. Questions? No. Okay. Right. So let's. Okay. So this is part 3 of our discussion of optimization, and I promise you the final part, modulo our redux next week when we talk about conjugate gradients. Okay, so now we are going to talk about the daddy of all optimization problems. This is the biggest, most general possible thing you could write down, at least if you lived before 1975. Of course, people think of all kinds of weird variations of this problem and stuff, but basically we're going to minimize the function f such that some other function g has to equal 0 at the optimum, and such that a third function h has to be positive. Now, if you thought minimizing an unconstrained function was hard, this is strictly worse. Right? We are moving into some really tough territory because I haven't told you a darn thing about f, g, or h. And in fact, the tools for this are usually very approximate and only work sometimes. It's a sad story. Of course, when things are convex, it's a different story, but oftentimes the story isn't quite as bleak as you might think. So, for example, and we'll see a couple examples in more detail in just a moment. For example, if I'm a company and f represents my profit, or minus my profit, because I probably want to maximize my profit. And G and H can encode different constraints on like how many materials I have and so on, right? Even if I don't find the global minimum of this optimization problem, if I get a better point than where I started, then I'm already happy because I just made more profit. Yeah? So oftentimes, even if we can't guarantee that we're going to reach the global minimum of f subject to g equals 0 and h is greater than 0, if we can find a feasible point that has a smaller value of f than where we started, that's still a good outcome for us. Yeah? The story isn't quite so bad. And in fact, oftentimes we can do really well. Now why is it hard? Well, we are simultaneously doing 3 different things. Right? 2 of which we just talked about for like 2.5 lectures, yeah? We're minimizing f, we are finding roots of g, and we're finding feasible points of h, that is, points where h is greater than or equal to 0. We have to do that all at the same time. Any one of these 3 problems is difficult on its own. Yeah? So we really shouldn't expect that these algorithms will succeed in all possible cases, but we're going to try and characterize some good behavior. Yeah? Okay, so let's see a couple examples of when we care about this. And in fact, there are tons. Unfortunately, sometimes problems just aren't linear, and this is life, and so we just need to embrace that and do what we can with them. So for example, how many people have heard of an implicit surface? Not a problem. So here's an implicit surface. It's x squared plus y squared plus z squared equals 1. Why is this an implicit surface? Well, you can define f of x, y, z to be just 1 minus x squared minus y squared minus z squared. An implicit surface is just a level set of a sum function. So this is all the points where f equals 0. Yeah. Now obviously this is a corny example, but there are lots of different implicit surfaces in the world. And in fact, in the computer graphics literature, there's a very common representation of just a generic 3D shape. We call this a blobby, which is corny, but it's from a cigarette paper in like the 1980s, and we're stuck with it now. And the idea of a blobby is that it's an implicit surface of the form to g of x equals some constant plus the sum over I of ai e to the minus b and x minus x of I. That's great. Great. So what did I do here? Well, these are all a bunch of different parameters. But basically, I make one big function f, and then I can let the artist specify these a's, b's, and c's. Right? And this is some function that we define the blob b to be the level set g equals 0. Right? And basically what this does is right, these functions are all little Gaussians, little bell curves. Right? So we set c to something negative, then near each of these xi's, we're going to push c to be positive again. Right? So what the artist does is places these little points x in different places so that sort of it takes c to positive, right? And then the outer boundary of this thing is a level set. If you Google blobbies, you'll see kind of what they look like. And then, as you might expect from the name, they're fairly globular. But even if you don't like that example, you can write down a circle this way, a hyperboloid, you know, and all of our favorite shapes from algebra class are implicit surfaces. In fact, any algebraic variety is an implicit surface, but that's not germane here. Anyway. So one very common problem in computer graphics, for example, if you are doing assorted types of collision detection, might be that you want to find the closest point from where you are to a point on the surface. Right? Well, how can I phrase that question? Well, so let's say I'm standing at point x0, so I can minimize over x, the distance from x to x0, such that I live on the implicit surface. This is an example of a nonlinear problem in general. Yeah? Let's see a completely different example. In manufacturing this time. I guess a little bit outside of the scope of robotics and graphics, but still a very important problem. Which is this. Let's say I'm running a company that has m different materials, and so for each material I have at most s sub I amount of that in stock. So maybe I have flour, eggs, butter, and sugar, and I have 3 pounds of flour, 10 eggs, 4 butters, whatever. And what do I want to do? Well, each of my products makes me some profit p sub j, but takes this amount Cij of material I. Right? So maybe cookies take some amount of flour, some amount of sugar, some amount of this and that, and then cupcakes take some other amount of flour and sugar and so on. And I want to figure out how many cupcakes and how many cookies and how many whatever else I want to make. Yeah? Perfectly reasonable business problem. Well, I can write this as optimization, right? So let's say the vector x contains how much of each product to make, right? Then I want to maximize my profit, which is just the sum of the profit per product times the amount I make of that product. Yeah? What are my constraints? Well, I better make a positive amount of each product. I think that's reasonable. And plus, I have to make sure that I don't exceed my supply of any one ingredient. Yeah? Very common type of thing that shows up in economics classes. By the way, this is a very particular type of optimization. Has anybody seen this before? What do you notice? There aren't any squares, there are no cosines, there are no sines, nothing. This is called a linear program. Okay, another problem. We already solved these squares, but sometimes, in fact, I was just helping a guy in the psychology department at Stanford who's working on some brain imaging problems. Right? And for him, he's trying to figure out which parts of your brain that some piece of software has identified are relevant and which ones aren't. Right? So once put little weights in front of them, that sort of, so your computer learns a little weight saying like, I think this one actually is a piece of anatomy and this is noise. Right? So in his application, a negative weight really makes very little sense. So one thing you might do is, write down our favorite least squares energy we've already talked about, but just simply add a constraint that all of your x's are non-negative. It's called non-negative least squares. Surprise. And this is another example where we're minimizing a function with, in this case, just an inequality constraint. Yeah. So as you can see, constrained optimization problems can take all kinds of different forms and apply to all kinds of different fields. In fact, in your notes, I go through 1 or 2 additional applications, something in computer vision called bundle adjustment, which involves basically I take a lot of different photos of an object from a lot of different angles, and now I'd like to estimate the 3D pose of that object based on these camera projections. But I don't know where the cameras are, I don't know where the points are, and I don't know where my camera is located. So I have to solve for all of this simultaneously. This is called bundle adjustment, and sadly it is a very common problem and a very difficult optimization to do. Cool. So a couple basic definitions. First of all, feasible point is one for which g of x equals 0 and h of x is greater than or equal to 0. So we're not going to look at our energy. A feasible point is one that satisfies the constraints. So obviously our job is to look at the function f, constrained to the set of feasible points, and find the minimum. Yeah? A critical point of a constrained optimization is just like a critical point before, right? Like a local minimum, maximum, saddle point, whatever. But in this case, you're only allowed to look in directions that satisfy the constraints. Right? So it might not be a global minimum of f. It might be that if I am willing to break one of the constraints, that I could get a smaller value of f. But within my constraint set, this is as good as I can do. So these are our basic vocabulary words. And today, our job is to derive sort of something similar to what you guys have been playing with a lot in 205. Hopefully you're getting better at it as we move on. Right? This is new to 205, by the way. We're gonna treat this instead of some ODE problems later in this class. This is very important in a lot of modern machine learning applications. Okay. So remember, we have used this tool to death now, which is Lagrange multipliers, which says if I'm trying to optimize f such that g of x equals 0, then I define this thing called the Lagrange multiplier function, right? And my critical points are critical points of this thing for both x and lambda simultaneously. No? Hopefully this is a familiar story by now. You certainly don't know it. But now we have this pesky h. And h is non-negative, but it can be positive. Right? This is a really annoying case, right? We have this constraint that h is greater than or equal to 0. So you might crash into the h wall, and you might not. It might be that that constraint is actually irrelevant. Yeah? So how do we deal with that? Sort of, that doesn't look like a calculus problem anymore, right? When you add inequality constraints, you don't expect to be able to take derivatives and set them equal to 0 and play the usual game. But in fact, Karush, Kuhn, and Tucker prove that we can. And so we're going to go through this a little bit. So remember, we have this constraint that h of x is greater than or equal to 0. And I'm going to break, so we'll call x star our optimal point. So we solve our optimization and we've minimized it subject to our constraints. And we got our point x star. And there are two things that might happen. Right? So let's take a look at a particular constraint, h sub I. By the way, how many people have seen KKT conditions before? Probably a few that have taken 229. How many people could derive KKT conditions? That's what I thought. Okay, so we're going to do that now. So for each, so remember h is really a vector, so we'll say h sub I is just the ith component of h. Yeah? And for each h sub I, we have two options. Either he is strictly positive, right? Or he's equal to 0. Because we know h is greater than or equal to 0. That was one of our conditions. Yeah? Well, we'll call that an active constraint when h is equal to 0, and an inactive constraint when h is positive. And in fact, these two cases are quite important. So, when a constraint is active, what do you think is going to happen if I were to remove that constraint? Well, chances are my optimum would actually move. Right? Because what's happened is, I mean, what you should think about, like for example, let's say that I have a constraint x1 is less than or equal to 0. Right? So here's the plane. Yeah, here's say x1 and there's x2. Yeah? So we have sort of this entire region here of feasible points. Right? But we can't go over there because x1 is negative. Right? So if my constraint is active, that means that, you know, I'm solving my optimization, whatever, and I crashed into this wall. Right? So chances are, if I removed this constraint, x1 is greater than or equal to 0, it might be that I could actually move somewhere into the bad land to get a better solution. Right? Somehow I crashed into that wall and it became an active constraint. Yeah? Now, what happens if my constraint is inactive? Well, that means that h is strictly greater than 0. Right? So that means that really I'm sitting somewhere inside of my feasible set. I'm not on the boundary. So what would happen if I removed my constraint? Well, probably nothing. Right? Because at least locally, I didn't have to enforce that constraint to get to this optimal point. Yeah? Now globally, it might be the case that there actually accidentally is secretly some other feasible region all the way over here, and I just don't know about that, but we're going to ignore this case for now. Yeah? So, an active constraint is one where if I remove that constraint, chances are my energy would change. An inactive constraint means that probably nothing would happen if I removed it. Yeah? Obviously, probably is a mathematically highly imprecise word. Okay. So here's going to be our idea for figuring out a differential optimality constraint. These are called the KKT conditions, which is that we can, if God had told us before we solved our optimization which constraints would be active at the optimal points and which ones would be inactive, then we could have played a game where we solve our optimization a second time, and made all of our active constraints equality constraints, and made all of our inactive constraints just removed. And we would expect to get the same point. Does that philosophy kind of make sense? You're either at the boundary or the interior. Okay. So let's formalize that a little bit. So, ignoring the fact that we have an inequality constraint, if in fact all of our constraints were active, we would have this Lagrange multiplier function all the way to the top. Yeah? And if I differentiate this thing with respect to x, I get this condition on the third line here. Right? This is just the gradient of the first guy with respect to x. Yeah? Familiar? No? I haven't done too much yet. Now, unfortunately, we can't use Lagrange multipliers in the case of an inequality constraint. We just can't. They're not relevant anymore. But we could cheat. Because we could say, okay, let's just remove all of the terms that are inactive and keep all the terms that are active. Right? So we know that if H had only contained the active constraints, then this still would be a critical point, and this condition is okay. It's just the inactive constraints that are getting in our way. So the really clever thing that Karush, Kuhn, and Tucker did was they said, well, we're going to assume that this second formula holds, but I'm going to add an equality condition that says the product of mu and H equals 0. There should be a vector over that 0, I'm sorry. I get used to typing that vector symbol. Okay, what does this say? Well, let's think there are two cases, right? We got to keep in our head, we got two cases all the time. The first case is that our constraint is active. What does that mean? That means that H is equal to 0. Right? Because our constraint was H is greater than or equal to 0. It's active, so H equals 0. So in this case, this guy is satisfied just automatically, and we're good upstairs. Right? The mu's satisfy the same as an equality constraint. And what happens when you have an inactive constraint? Well, that means H is greater than 0, but then because I added this constraint, mu has to be 0. Right? Because it's the product of two things equals 0. So what happened? Well, if I'm active, then it figures into the Lagrange multiplier formula on the second line here. If I'm inactive, then by adding this constraint, I zeroed it out. Because at least one of those two guys has to equal 0. Very clever. So in fact, the KKT conditions say, okay, it's not enough to just satisfy this differential optimality condition on the second line here, right? That's just the Lagrange multipliers formula. But if I add this second formula as a constraint, this is a system of equations, then we're still good. Very clever. Now, of course, there's one remaining question when you derive KKT conditions, and I'm likely to get this wrong, so I'm a little nervous. But so far, my discussion has not distinguished between Hj being greater than or equal to 0 and Hj being less than or equal to 0. Right? All we talked about is whether I'm touching the wall or whether I'm not touching the wall. So obviously, I'm not quite there yet. We're missing something. Yeah? So let's say I'm standing at a point. Something that I do a lot when I talk about optimization. Talk about, when we talk about differential equations, I'm waving my arms around. Anyway, so I'm standing at a point x star, and I'm looking at my feet. There might be a direction I can move that decreases f. Remember, I want to minimize f? There might be a direction that can make f smaller, but we know that that direction is going to violate my constraints. Right? Because if it didn't violate my constraints, I would move that way, and this wouldn't be an optimal point anymore. Yeah? So I'm standing at my feet. The direction that decreases f the most is minus grad f. Right? This is the gradient, the steepest descent direction. We already talked about that in class. And remember that h cannot be negative. Right? We have a constraint that h is greater than or equal to 0. So what I'd like to say is when I'm standing at my feet and I see a direction that decreases f, then if I were to walk in that direction, I would violate my inequality constraint. Right? Well, the direction that decreases h is minus grad h by the same argument. Right? So what I'm saying is, if I move in the minus grad f direction, then I must also be moving in the minus grad h direction, because that way h is decreasing, which is breaking the rules. Right? H has got to stay greater than or equal to 0. Yeah? So I can express that in a very simple way, which is this. That if I take the dot product between minus grad f and minus h, I cancel the minuses, then I better get a positive number. Right? This says that if I move in the minus grad f direction, then I'm going to decrease h as well, and that is against the rules, and we can't do that. Right? So we're going to add this inequality constraint. Now for those of you that have seen the KKT conditions before, you're going to say, but Justin, this is not the KKT condition I know and love. And indeed you're right. In fact, really, this is a very difficult condition to work with, right? You have to differentiate two different functions, multiply them together, and check that it's positive. That's a tough thing to enforce. Yeah? But thankfully, we actually can do a little bit better, and in the remaining 10 minutes, we'll see why. Where did my eraser go? There. Okay. Can I erase our picture? You guys see the difference between an active constraint and an inactive constraint? Okay. Ugh. By the way, there are lots of different derivations of the KKT conditions. This is my own, which probably means that it's garbled. If you need links to other ones, there are plenty of other ones online. I can try and find you a few. Okay. Anyway, so where are we? Great. So we want to enforce that grad f of x star dot grad h of x star is greater than or equal to 0. What this says is that the direction in which I could increase f, or decrease f, is the same as the direction in which I would be decreasing h, and that's against the rules. Right? Really, this should be hi for each constraint I. Yeah? Okay, but we'd like a better condition than this, right? One that's not quite so yucky. And I don't think I'll put it in this. So, let's go back to our first order optimality conditions. So remember when we did our Lagrange multipliers thing, we have that the gradient of f at our optimal point x star is going to be equal to what? The sum over I of lambda I star. We'll say that we went ahead and finished our optimization times grad g I of x star plus sum of j mu j star grad hj of x star. By the way, this is only the sum over active constraints. Okay? Because what happens in an inactive constraint? Mu is equal to 0. It just goes away. Right? That was what we did by fiat. We wrote it down and we are enforcing that condition. So anyway, there's our sum. Now, in fact, I claim that it's always enough only to deal with inequality conditions. This is not a numerically stable thing to do. But one thing I could do is enforce two inequality conditions instead of one equality condition. For example, if I want g of x equals 0, I can say that's the same as g of x greater than or equal to 0 and g of x less than or equal to 0. Again, obviously numerically a poor decision, but for math it's perfectly fine. So for now, I'm going to assume that I did that ahead of time, and that I put all of my things into h, right? So we can kind of ignore this term. Cool? It's a trick. By the way, you could go back through this proof and carry this thing around, but it's just like dead weight. Okay. Right. So what am I going to do? I'm going to do a really cute trick, which is I'm going to take the dot product of both sides of this equation with the gradient of h sub k. Remember, I have all of these different inequality constraints. I'm just going to choose one, h sub k, take the dot product of both sides. Okay? So, in fact, I'm going to swap left and right in that process because I'm going to simplify one side and not the other. Yeah? So, in fact, what am I going to get? Well, I will get the sum over j active of mu j star times grad hj of x star dot grad hk of x star. Yeah? That's this thing, dot